This is the 13th of a series of videos about complex analysis, and in fact the sub-series is about complex arithmetic, and it's also part 13 of that series. I'm also focusing on using Mathematica to illustrate the ideas from complex analysis. In the last few videos we looked at some important properties relating moduli and arguments of products and quotients to the moduli and arguments of the factors and the things you're dividing. In this video, I'd like to look at those same facts from the viewpoint of what's called the polar form of a complex number. It might be good for you to go get a piece of paper, pause the video, and when you are back with a piece of paper, go ahead and multiply out by hand these two complex numbers and see what you get. I will go ahead and do it on the video as well. We've got fairly complicated looking complex numbers there because of the roots. Let's get a little practice with root manipulation as well as complex number manipulation. So here is the product that I'm trying to compute. And when you're doing this by hand, you should use the FOIL method. First times first is square root of 8 times square root of 3. That's the same as square root of 8 times 3, which is square root of 24. Outside times outside is square root of 8 times I. Inside times inside is square root of 8 times square root of 3 times I, which would be square root of 24 times I. And last times last is going to be square root of 8 times I squared. I squared is -1, so that'll be minus square root of 8. Alright, now these roots can be simplified. First of all, we can also combine the real parts and the imaginary parts. So the real part of this answer is going to be square root of 24 minus square root of 8. Both of those radicals can be simplified. 24 is 4 times 6. Square root of 4 is 2, so I can write the square root of 24 as 2 times the square root of 6. Think about that. Work it out on your own as well. Square root of 8 is the same as the square root of 4 times 2. Square root of 4 is 2. So this can also be written as minus 2 square root of 2. That's equal to the square root of 8 there. And then the imaginary part is square root of 8 plus square root of 24. Essentially the same thing as this except with a plus sign in it. So I'll copy and paste to get that and change this to a plus. Alright, so that's what you should have gotten. You can factor the 2 out of each of these things if you like. You could also factor the 2 out of the entire complex number. Let's just go ahead and leave it as it is, and let's see if Mathematica gives us the same thing when we do z1 times z2. Actually, when you just do it like this, it will not look the same. It, in fact, didn't even expand it, but if I do complex expand, nested in that command, then it will expand it and simplify a bit. And if you compare, this indeed is the same thing that we have here. Alright, so that's what it is. You might wonder, what is that approximately? It's approximately 2.07 plus 7.72i, 7.73i, when you round. Let me visualize that with the same kind of visualization we've done before. I'm starting my locator points at the numbers that I'm multiplying, square root of 8 plus square root of 8 times I, and square root of 3 plus I. See it in here, so here's square root of 8 plus square root of 8i, and down here is square root of 3 plus I, and up here is the product that was about 2.07 plus 7.73i. 2.07 plus 7.73i is the product. So it's a fairly complicated product, seemingly, but it's actually not quite as bad as it looks, and in fact there's a better way to represent this product that is simpler. And that's to go ahead and think of it in terms of its modulus and its argument. Let me first think about z1 and z2 in terms of their moduli and their arguments. Something you should be able to do by hand as well, and looking at the picture. The modulus of z1, its absolute value, so to speak, turns out to be exactly 4, and you should check that out. You get the square root of 16 ultimately. And its argument, this shouldn't be surprising, it's 45 degrees, or pi over 4 radians. How about Z2? Think about it. Maybe use the formula. Maybe even try it in your head. You should get square root of 4 or 2. And its argument, you could look at the picture and guess, should be 30 degrees, which is pi over 6 radians. So, by these facts up here, in particular this one and this one, the product of Z1 and Z2 should have a modulus equal to 4 times 2, or 8, and should have an argument equal to the sum of pi over 4 and pi over 6. If you get a common denominator of 12, this would be 3 pi over 12, and this would be 2 pi over 12. You add those together, you're going to get 5 pi over 12. Let's see if that happens. So, again, the modulus of this should be 8. Need to simplify, though. Simplify. 8. And its argument should be 30 degrees plus 45 degrees, 75 degrees. It's also 5 pi over 12 radians. There we go, 5 pi over 12. It's also helpful, based on this, to rewrite the product symbolically in another form. Using the fact that, let me put it up here. Using the fact that using SOHCAHTOA from trigonometry, you can write x equals r cosine theta and y equals r sine theta, where you don't have to think about this in terms of complex numbers, or if you're thinking points in the plane, if r is the distance between the point and the origin, and theta is the angle between the ray going from the origin through the point makes with the positive x-axis, these equations are going to be true, certainly in the first quadrant, but it also turns out in the second, third, and fourth quadrants as well. And because of that, you can use the argument and moduli of these complex numbers to rewrite them in a new way. For example, Z1, this one here, could be rewritten as 4 times cosine of pi over 4 plus I times 4 times sine of pi over 4. Do you follow that? Draw a picture. Think about drawing the triangle. Same triangle as you see here. This one here. Label your hypotenuse with the number 4 and your angle with pi over 4. Think about these equations that come from trigonometry, and think about the complex number, the fact that it's square root of 8 plus square root of 8i, and you're going to realize this is another way to represent Z1. Doesn't look quite the same if I complex expand it out. Maybe to multiply that square root of 2 through. I guess it didn't. Oh well, it is the same. 2 times square root of 2 is the same as square root of 8. And likewise, if I think about Z2, its modulus was 2, and its angle was pi over 6. So this is another way to represent Z2. And that is square root of 3 plus I, the same thing. And how about the answer? I know the answer had a modulus of 8 and an argument of 5 pi over 12. Let's actually put it down here. So this should be the same thing as this. So let's see, maybe if I simplify it, it'll look the same. Complex expand it. You can nest these things. There we go. This is exactly the same as this. So that's a little introduction to the polar representation of a complex number. We'll continue with it in the next video, where I'll introduce something called the cis function and also hint at something with exponentials that's related to all this.